Good morning. I hope you are enjoying this conference as we are. This is our second time here and the first time presenting. So we want to thank AnyLogic for giving us the chance to show one of our models. In this case, this is, as John mentioned, it's a model that we built for a company that manages the barge operation in South America, and the largest river in South America that goes from Brazil to Argentina, going through 4 different countries. Particularly, this project was a bit different from the project we usually do as a SAP partner, but we were called by this company some years ago, and they needed to replace, as usual, a very large Excel file they used for their 5-year planning. And they couldn't work anymore with that Excel. That was too complex to maintain. It didn't run. So they wanted to see if they could replace that with a simulation tool. So the model you're going to see now is our 3rd generation of that first proof of concept we did with this company. And what we changed in this last model is that everything is a parameter, so you can basically adapt the model to any barges operation. So this is allowing us to even use it here in the U.S. in the Mississippi Ohio River, where they're a very big barges operation. So this is the list of topics we would like to cover. I will do a brief introduction of ITE, of our company, and then I'll leave Elisa to present the model. From ITE, we come from a slightly different angle from the companies that we see are working in simulation and the presentation we have seen here. Basically because we have been working for SAP as a partner for 16 years, and we have specialized in the implementation of planning solutions within SAP. And this allowed us to implement solutions in different industries, like pharmaceutical industry, retail, or production companies in different parts of the world. So we have been implementing solutions in Europe and all Latin America and here in the US. And once you are in the company and you are working with the planning solutions, every planning process needs a what-if scenario. So this puts us in a very unique position to introduce the simulation as a what-if scenario. So what we have done in the last years is we developed a few template models that we usually need in our planning processes when we implement with SAP, because we found that it is easier to engage a client, a CFO, or the responsible for the sales and operation planning when you have something to show them than when you go with just talking about the simulation concept. That's a long-term process. So we developed some solutions in 3 different areas. One is the sales and operation planning, the logistic model, and we have market research and product launch simulation for pharmaceutical companies. And the way we present this to our clients, for example, in the sales and operation planning, that's the typical implementation we do in SAP. Here we have 2 different models that we can use to complement as a what-if scenario in this planning process. So when the user is working on their demand plan and they're building blocks from marketing and finance, and they have to they need the input from the operation people. We have a model that would run a rough capacity simulation based on the demand plan, and would immediately give them a feedback if they're able to produce what they are expecting to sell. So that's like a template we can easily plug into SAP. It already has the interfaces for SAP, so it can read and write to SAP. And once the process is finished, there's another model where they can simulate their P&L and evaluate different macroeconomic variables, because usually these are multinational companies that have operations in different countries, so they need to see the impact of macroeconomic variables in their business, like especially when they're working with Latin American countries where the inflation changes a lot, and the exchange rate or the GDP growth is different from country to country. So this is the way we present the simulation models to our clients. This is a list of some of our clients and projects that we have developed, and as you can see, there are a lot of pharmaceutical companies, and we have worked for Novartis or Sanofi-Aventis in many different countries. And there are a few manufacturing companies, and what we would like to focus now is on the simulation model that we built for Interbarge. That's the larger barges operation in Latin America. So, Lisa?
Well, this waterway, this inland waterway, spreads along 2,200 miles and allows the transportation of a wide amount of goods of agriculture and different commodities that go from upstream in Brazil to downstream in the River Plate. All these commodities are transported by different operators. Interbarge, our customer, is one of them. And they move this freight to the processing areas and to the export terminals, trying to do it in an efficient and reliable way. Commodity traffic in the waterway region is estimated to have grown since 2000 from 59 million metric tons to 93 million metric tons in 2014. And this is a business that is still growing. This dynamic region benefits from the growing needs of commodities worldwide. So Interbarge activities includes transporting all these commodities to the crushing plants located in the river, down in the river, and to the consumption areas. So which is the problem that we are addressing and why they were looking for a solution? They could not plan really the short or the long-term operation with a good degree of precision. They have all these Excels, but they were not able to plan it. Why? Because this operation has a huge amount of variation. It has a lot of sources of variations. The operation has two modes. I just want to go a bit into this just to understand the way we have to simulate it. The operation has a charter mode and a spot mode of dealing with it. What do each of them mean? Within the charter operation, the waterway operator, the Interbarge, the customer, commits to a certain customer a fleet. It means it commits the push boats and the barges, and we only transport the freight of this customer, of the contract they have committed to. Some of these contracts that they commit, they leave free space when they are going upstream or downstream, because some of these customers, they only need to move freight downstream. But they have this free space, and they allow the operator to use this free space when they have it. Sometimes this free space that we are speaking about is during certain periods of the year, because as we are speaking about transporting agricultural goods, They are not always, all the year round, you have the offer of this freight. So there are certain periods where you have free space also to be used. And sometimes you have free space while building the convoy because perhaps you can have the power within your push boat to push 20 barges, and you are only the contract that you have, it only takes you to push 10, and you have this power, this capacity, that you also can use it to make a better profit of your business. So all these free capacities may be used, and it is desirable to be able to quantify its potential. And it's very difficult if we are not able to simulate what's happening with the activity. Within the spot operation, the other mode of operating, push boats and barges are free resources, and they only commit to on-demand contracts. It means that they will transport a certain freight in an expected period of time. So the company decides, Interbras decides, according to the geographical location of its own resources and the expected delay of the availability of the resources, which freight to move. There is also another variability in the freight offer along the year, as I mentioned, and there is a great variation of the resources location along the year. What I'm trying to explain is that the input of this activity is not that we have routes that they are decided. We have the resources, and along the run, we have to decide which is the contract, the most profitable contract that we are going to load on our barges, and the most profitable barge that we are going to push with our push boats to get the best revenue. So each time that we are moving along the river and we are arriving at a port, we have to review what happens. So which was the challenge of this model? Really understand the risk of the operation. They were trying to be able to simulate the decision logic along the operation, and this decision logic is changing. The answers that we were looking for is how to combine resources, where to locate them, the maximum delay suggested for waiting for a convoy, using or not fleeting points or hubs to avoid delays, using different push boat sizes for different river sections. So all these variables have to be combined. They are time dependent, and they are cost dependent. All these variables could be evaluated looking for the ideal fleet if we could have a realistic model that simulated the whole operation with probabilistic distributions for stochastic variables. So this was really our challenge, to be able to have a realistic model that simulated the whole operation, which was the final goal for our customer, to maximize the net voyage revenue. So the company decides, according to the geographical location of resources and the expected delay of availability of resources, which freight to move. In this way, with a model, we would try to find which was the net voyage revenue in the short and long-term plan. Now, how we developed this model? Barges and push boats were designed as moving agents. They have a certain geographical starting point. They can be in a port or navigating with a certain assigned route. They have characteristics such as speed, loading, capacity, fuel consumption, draft. All these are related to the operation restrictions. They have state charts that show the different states in which the agent may be, like loading, unloading, navigating, waiting in a queue, shifting convoys, waiting for refuel. And then we have other two kinds of agents, contracts and ports. Contracts have all the information about the route, the freight, the price. State charts show the different state in which the contract may be, active, inactive, completed. and ports have been modeled as discrete event flows where barges and push boats queue for shifting the convoys, queue for loading, for unloading, for waiting for a viable barge, for refueling, all the activities that barges and push boats must do in the ports. You have to take into account that in the ports we do not only have our own barges and push boats, but also the competitors. So the timing that's happening in the port and the delays that we are having, that's respond to certain probabilistic delays and times, and it must be taken into account, but because they may reformulate the decisions of the routes that the push boats they are going to follow. Ports also have draft limitations and delays and are estimated based on probability distribution, most of them. Here's just a schema where you can see all the different agents that we have related in our model. Well, now, barges, when empty, they have to decide which contract to assign to and which freight to load. This does not come as an input. It's the only input we are loading from Excel. It's all the barges that we have, all the resources, and all the different offers that you have in all the ports. But the barge, we do not know which is the contract they are going to load. Push boats, when arriving to a port or a fleeting point, decide the following route according to which convoy they will push. Each arrival to a port or a fleeting point implies a new decision for the push boat. It means that the push boat only has a route assigned from port to the following port. We do not know if that push boat will go all the river long or it only go up and down. That will depend on the equation we are going to explain as we calculate. So the decision process is the core of this simulation with all these moving agents, because we have to input to all our agents what they have to do. What we build it is a simplex matrix where an iterative function will allow to find, according to the maximum delay time schedule for a certain scenario and the maximum convoy size according to river limitations, the best route for that push boat. So we will iterate through the different numbers, through the different metrics, and try to find which is the best decision for that agent. So once all data from Excel or database is loaded, agents are created and situated in the corresponding geographical location, and then we have a tree of logical decision functions that have been built. One tree is for barge decisions, and the other is for push boat decisions. When barges arrive to their final port, they have to decide which is the next best contract for themselves. There is a chance that the best contract option be in that port, or perhaps the best revenue is with some freight that is located in a port nearby. So each time barges that are free of freight have to re-evaluate, iterating through all ports and contracts, which is the best option according to what? To their maximum TCE. The TCE is the time charter equivalent. This is the key indicator that responds to an equation that will allow us to decide which is the best option. This problem has been solved with our model code and a sequence of functions that iterate through all the barges and contracts, calculate the time charter equivalent related to barge contract, and find the highest estimated time charter equivalent for that barge. Once this simplex matrix is solved, barges will load their freight if they are in the correct port, or they will wait for a push boat that will push them to the loading port if they have to load their freight in another port. It means that when the matrix is solved, barges go to an assigned status within the state chart of of our agent, and keep in that way until they are loaded. They move through the river, and then they unload their freight. With push boats, decision logic is a bit different from that from barge. Push boats, when arriving to a port internally, they free themselves from the convoy that they have and review the possible following routes. It means that the defined route for a push boat is only until the next port. It decides solving also a set of equations and iterations with the time chart equivalent, but in this case, barge push boats as indicator. Which is the best, they choose which is the best convoy option, and once chosen, it will define which is the direction of the future navigation. If it goes north, south, east, or west. It's not the other way around. It means that they first choose which is the best time chart equivalent option for themselves, and then with that, they define the route. So we let the agent know in which way they have to move along our model. So we have built these internal functions that solve all these time charter equivalent equations. If there is more than one push boat option in a port, we have to take into account all resources nearby. And the model will choose which is the best convoy option, again, according to the best time charter equivalent push boat convoy results. We're always using this indicator that it's different for the relation between barges and contracts, between barges and push boats, and between push boats and convoys. But it's always solving this equation that it's related to the geographical location of our resource, because it's completely cost dependent at the distance where we are located. So the time chart equivalent equation changes depending on the location of our resource. So within the model, we have to look where in that moment the resource is located. We input that information into our tree of logical decision equations, and we solve the simplex matrix that allow us to decide where the push boat or the barge will go. Once we are ready to run the simulation, variables and restrictions can change, so we can upload different scenarios. This kind of operation also is interesting to run it with different water levels, because when we have to plan a 5 years long-term operation, we know that the water will modify, the water levels will modify. That means that in certain periods of the year, some of the ports will not be possible to operate with the push boats that have a bigger draft. We need shallow drafts of the push boats to be able to operate on those ones. So as the operation has a long-term plan of more than 5 years, running different scenarios allows us to estimate the risk of the operation. So what are we looking for? What we have been doing is we run this model with different scenarios, not only of water levels, of different port delays, and once we get all this information, we can estimate the variance of the operation, the highest and the minimum risk of the whole fleet operation, and we are able to deliver the projection of maximum and minimums of the expected profits of this. Okay, I'm going to move a bit quicker to allow some time for the demo. This is some of the equations that we use within that simplex matrix. So we will input, we calculate each of them, and these are the inputs to look for the best option. And here are some of the indicators we deliver in the output of the model. One of the outputs, the most important for our customer, is the exported Excel that we provide, where you can visualize the proposed operation plan for each push boat and barge. And with this, you can, again, analyze the risk that you're having. You can negotiate a better price for the freight that you're going to commit to. And while you have a lot of other indicators that are very useful for the analysis of our customer. Well, now I'll let David show you a bit of our model running. Thank you.
So these are some of the scenarios that they run with the model. The two most important scenarios are the long-term planning, the 5-year planning, and the short-term planning. Because when you create the agents, you load each barge and fleet push boat. You can load the location, and if it already has a contract signed, and if it's navigating from which port to which port, and what is the speed, and what is the exact location. So what they can do is take their real data from today, make a 45-day plan, starting from the existing position of their fleet. When they do a 5-year planning, they choose where to put the barges. So these are two very different scenarios they can use the tool for. As you can see, this is the GIS, the map with all the ports where they operate. There are some parameters that the user can change to activate or deactivate some of the logic in the system if they want to use it in a simpler way or more complex way. But once they start running the simulation, the barges will be in the right position, and they will start deciding which contract to take. And you can see the barges moving through the rivers and stopping and loading in different ports. And you can see what is the situation for one specific push boat. So this is the state chart for the push boat, where you can see if it's navigating, if it's assigned, if it's pushing boats, or if it's waiting. You see a chart down here where you see the time it's occupied, the time it's waiting, the time that it's navigating. And you can see all the push boats you have in the system. Same thing for the barges. If you click on the barges, there's a similar state chart for the barges, and you can see it's moving. Well, it's about to finish now. But the barges will show if it's assigned to a contract, what is the contract, if it's loaded, what does it load, how many tons, and it would accumulate the tons. And so you have information of how this barge was used during the entire period, and what was the occupation, how many tons you transported. So there's a lot of metrics that they can take from the simulation. The same way you can see the different contracts that you have available. And these are, as we said, there are some contracts that are fixed contracts that you have to complete. If not, you have some penalties, and there are some spot contracts that you can decide if you want to fulfill or not. And there's some information here on the tons that have been transported for this specific contract. Contracts could go into a standby mode if it's a period of the year where they don't provide freight. And there's also a probability distribution where we just don't offer this contract. So that simulates the competition. If someone else took that contract, then we don't have it available for us. So there are many options with stochastic variables that are operating in parallel. So if you look at a port, this is a discrete event process where you can see the loading process, the unloading process, the fleeting process, and you will see all the barges that went through the port that are in the specific queues, and how many barges were loaded or unloaded in a port. So there's a lot of information as well from the ports. There are many costs related to the ports for the waiting times, the shipping times, and shifting times, sorry. And there are also some penalties if the port doesn't provide finish the loading or unloading process in time. So the model in total has, I don't know, more than 300 different variables and restrictions that even the flag of the push boat or the barge could restrict where it can operate. So if you have barges with a Brazilian flag, it could maybe not load or unload in Bolivia or in Paraguay, and there are many restrictions that we have to take in account when we are deciding.
Thank you for that. I just had a quick question about the weather constraints. For like the long-term planning, do you take in historical weather conditions to then forecast what could happen if there was, low weather for a long period of time?
Yes, they have a lot of information of, historical information that we run some statistic analysis on those, and we created the probability of distributions for those.
Yeah, we first analyze the data and we fit it to a certain distribution of them. We get the variance of that. The average, it depends on which fit it to each of them. And we loaded that data in each of the delays that we were having, even in the long term in the same way. And the same thing with the water, with the different water levels that we have different curves along the year. It depends on which month, in which week of the year we are, that is the water level of the different ports, and that acts as a restriction within the model.
In the model that we are using here in the US, there's also a chance to add storms, like winter storms that would affect some ports and the speed of some of the convoys. And that's something you can activate manually, or you can just use a probability of distribution to see what would happen.